amplitude, your B is your frequency. How many complete curves in 2 pi? Therefore, your period is always 360 divided by that, or 2 pi divided by that. Sometimes it's easier in degrees to think of that. And then you can say, okay, if I need to complete 2 cycles in 360, then each one has to be 180. There's your period at pi. So you can figure out your amplitude, your frequency, and from that you can get your period. And if you do it the 360 divided by 2, that's okay with me. You could know later on that you can flip that, convert that back to a radian, and do it that way. Aaron?
When the curve goes like that, that's one.
It has to be a complete cycle. If this is your sine, it's got to come up, down, stop. Up, down, stop.
That's 2.
That's 2. So it takes 180 to complete one of them.
Oh, okay.
You have to go through 4 quadrants. Remember, you have to go through 4 quadrants. 2 positive signs, 2 negative signs. So this is a good help when you see 2 positives, 2 negatives. Chris? Oh, go ahead.
And you just divide 360
By 2. Because it takes you 180 degrees to complete one of them. Chris?
Do you have to, for the period, do you leave it in radians?
Well, normally we do leave it in radians, but if you have trouble converting it, think degrees. And then you can always transfer this back to radians if you have to. As long as you can kind of give me the period, even in degrees, I'm okay with that. Because sometimes it's easier to say 360 divided by 3. If I say 2 pi divided by 3, and you're looking at 2 pi over 3, and you don't convert it in your head, what does that mean to you? Really nothing. But 360 divided by 3 says, oh, every 120. I know I'm right past the 90. I'm going right before the 240. It makes a little bit more sense. Because degrees are easier to match up on your calculator. Radians are not, because radians convert it to a decimal. It doesn't show us your radians. Okay, these guys, if it helps you, pull this out to be 1/2 x. So that there is my frequency. This is my amplitude. It's going 2.5, 5 over 2, 2.5 up, 2.5 down. There's my frequency, a half a curve in 2 pi. So if I only can complete a half a curve in 2 pi, I need another 2 pi to complete my curve. The cosine makes that U look. Okay? Now, if you remember with your cosine curve, you get a positive, negative, a negative, positive when you go around your quadrants. So that's why it looks like this. And if you say 360, be sure you keep change, flip this guy. Because, and if you just kind of think about it logically, half in 2 pi, another 2 pi to complete. Okay, amplitude, now this was in pi cycles. So if your frequency is pi, every pi you will make one. It's easier to divide 2 pi divided by pi. So it's actually your period is 2 radians. It just is a way of like looking at the radians. Remember when you convert your pi is 3.14. So if you divide it in 2, I think it was like 1.7, 1.5 something or other. So you can kind of get a feel for that. This guy, most importantly, your amplitudes can only be positive. It's your distance. So make sure you take the absolute value of that. What is this negative actually doing to this sine curve? It's reflecting it. So instead of going up, I'm going down first. Okay, it's making me go the opposite way. It's reflecting it over the x-axis. Again, your frequency is 1, so it takes you 360 degrees or 2 pi to complete one cycle. And you can always put these on your calculator, double check them on your calculator. Okay, 19, again, if it's easier, pull out the 2/3 in front. This is saying to you, I can only complete 2/3 of my curve in 2 pi. I didn't go all the way around yet. So it's got to take me longer than 2 pi to complete it, right? If you think of it this way, 2/3 in 2 pi. So 1 pi, 2 pi, 3 pi would give you the other third. right? If you think about it logically, it'll help you out. Otherwise, use your rule, and you can use 360 divided by 2/3. Put that in your calculator, and that will give you what, 450, 360, and 180. 360. 540. 540. Number 29, go off this curve here. You had a basic, this is your basic cosine curve first. Then we jumped up this way, amplitude of 2. We kept the same period. We only have one complete curve. So you've got a frequency of 1. Therefore, the amplitude of 2 caused you a stretch. When you go like this, that's a vertical. If you go across, that's a horizontal. So we had a vertical stretch by a factor of 2. Everybody can find their transformations. Okay. 30. You again, here's your black curve over here. That's your cosine. That's your core graph, your parent graph. And you didn't change your amplitude here, but you changed your frequency. Your frequency meant 1, 2. You have 2 frequency. You kind of pushed it in like this, like an accordion. You pressed it in. So horizontally, you have a shrink. You used half the period here. Instead of using 360, you used 180. This guy, again, see the black curve? There's your sine curve. There's your parent graph. It shifted this over. Now, we didn't really get a chance to talk about the horizontal shift, so we're going to talk about your horizontal shift now. But your horizontal shift, depending on which way you go, will give you back a sine or a cosine curve, the opposite. This one happens to go the opposite way. Had they shifted the other way, you would have seen your cosine curve. It just went 90 degrees to the right. We didn't talk about your shift yet. So if you didn't get that one, I'm not so concerned about that. We'll talk about that in 1 second. Okay, here's your basic sine curve again. Now, watch what happened to that sine curve. It got moved up. It's a vertical shift up. What you're looking at is, where is this resting point? If I make my axis be here, isn't this the same as being down here, my sine curve? Find your axis, your resting spot. Now, count from here to here. You moved everything up 2. You moved everybody up 2. So if your range went like this, and you added 2 to everybody, you are now going from 1 to 3. Isn't that from 1 to 3? You took a vertical shift up 2. I gave you the transformation rules. The transformation rules in trig, kind of like the law of things, sometimes they're not as recognizable, but there's your vertical shift out here. And the fact that they went to 4 pi to complete 1 cycle, that means how much of that did they do in 2 pi? Half of it. So therefore your frequency was a half. Your frequency was a half, so you have a horizontal stretch, and you have a vertical shift up 2 units. Did you guys get that one? Yeah, you kind of have to look at it one piece at a time. I like when they give you the graph of something, because you can kind of like lay out where's your 2 pi, where's your x-axis, move that up. That's a good transformation. Whenever you do your sines and your cosines, find your resting spot for that, and then work the translation from your x-axis. It's easier. It's harder to go from here to here. I like to just find the resting spot. Look where I translated my x. Now, 39 is called the phase shift. We're going to add a little letter in here. So we're going to do a sine bx plus or minus c. So what happens is, this is the 1, that's the b, this is the c. So your phase shift says c C over B. And what this is saying is, just like this is like your transformations, just like you did this. Remember how we did a shift here? We did a horizontal movement 3 to the right. We always went the opposite way. That's going to happen here. This is like your horizontal shift. You know, we just did a vertical shift +2. Well, to get your horizontal shift in trig, we call it a phase shift. It's still a horizontal shift, but we call it a phase. So we do C over B. So we take this guy, we put it over there. So actually, this is your 1. And if we do the same thing that we used to do this, you know how it went the opposite direction? So this goes pi over 2, 90 degrees to the right. It's the same as this guy. Same thing. So that's what we call our horizontal shift over. Okay? What it does is this. Your curve, your cosine curve, went like this, from 0 to 2 pi. Now I'm going to move this. I'm going to start it here. I'm going to make my same curve, but I'm going to shift it over. So if you look to see where is my full cycle, an easy way to do that is this. Start it where this one used to be, 0 to 2 pi. And plug this in. So now, if I say where is one complete cycle, you say, okay, then it has to start at pi over 2, which we said it'll start at pi over 2, and it has to go past the 2 pi. When I add this to this side, convert this to the same denominator. So 4 pi plus 1 pi is 5 pi over 2. So do you see in here? It's still going to be minus. It's going to be 4 pi over 2, which is 2 pi. It'll start 90 degrees to the right. It'll end 90 degrees to the right. That's where my full cycle goes. You're awfully quiet. You're saying, what the heck is she talking about? Okay, probably much easier once you see a graph. Now this guy too, even though we call it a phase shift, if you followed your transformations,
Oh, we don't have 42.
we didn't have 42? Okay. Okay, these guys, were you okay with this? This one just changed the amplitude. Vertical stretch. When you stretch this, don't forget to change your range, and your range is going to change here. Just your range is going to change. This is a vertical shrink. Don't forget to change your range. 1/2 x, pull out your 1/2. Your frequency is 1/2. If 1/2 of your curve is in 2 pi, I need another 2 pi, 4 pi to complete my curve. Did I give you 49? Okay, 49, if you match up your transformations, is the same as a horizontal movement. So remember, it always goes the opposite way. In trig, we just happen to call that horizontal movement a phase shift. We're shifting the phase over, which still works the same way as your old horizontal movements go. So this is 45 degrees to the right. So now my curve starts 45 degrees to the right. If I want to know what it takes to get a complete 2 pi curve, I set this equal to 0 and I set it equal to 2 pi. So I have a horizontal shift. That part you should have been able to get, the horizontal part. We call it a phase shift, but a horizontal shift is what you're looking at. It's in parentheses, it goes the opposite way. So instead of starting my curve here, I'm going to start it right here at the 45. So I'm going to be a little bit off on my curve. So I need from pi over 4 to 9 pi over 4. It's just like taking your first one and say, okay, add 2 pi. Just add 2 pi to this, because doesn't it take me 2 pi to complete one? Or take 45 and add 360 to it. Sometimes it's easier to look in degrees. So this would be from 405, from 45 to 405 degrees. the horizontal part you should have gotten, because that's your regular transformation. Okay? And I crossed off the other ones, I think, right? Or I didn't. Did I cross off the 55, 63? Okay, because I didn't want you to go any further than these. I don't want you to do the ones with the double ones. That's harder. This one's fine. There's your amplitude is 8. You have a, what's that negative give me? Reflection. A reflection in your x-axis. Okay? That's what that negative does. Again, you have a phase shift. It goes in the opposite direction. So you're going to go pi, or 180 degrees, to the left. That should be your horizontal shift. That's called your phase shift. And if you want to know then how long will it take you to complete 2 pi? If you started at the negative pi, you're going to go to the positive pi, right? Does that make sense? To complete a full cycle? If I moved you back from 0 to negative pi, if you added 2 pi, you'd get to the positive pi before your cycle is complete. And this one, if you wanted to, remember we used to move the other ones over, make it easier, because the negative does the reflection. And this is a vertical shift. That will give you your vertical shift. Your period, again, is in radians. And I didn't care about those guys, because the phase shift is a little bit different on those. What I wanted you to catch is the regular shift in here, the horizontal shift. Okay. Questions? No? All right. Today we got a couple of things to do. Function, guys. Your tangent function works a little bit different because it is not a continuous curve. And the reason being, when we make your unit circle, pretend this is a unit circle. When we make your unit circle at the 90 and the 270, when you divide y divided by x, you're dividing by 0. And we can't divide by 0. If you went to your calculator and you said tangent of 90, it says undefined. It might even say cannot divide by 0. So at the 90, at the 270, we have asymptotes. Very similar to your asymptotes that we did with your other functions whenever we had something in the denominator that we couldn't use. So we have asymptotes here. Now, if we took a look at your tangent function, say we looked at 45 and negative 45. The tangent of 45, does anybody remember what the tangent of 45 is? 1. And it's therefore the tangent of negative 45 down here would be negative 1. So, if we did this, here's my 1, here's my negative 1. Your tangent function goes like this. And it rides along that asymptote. And in each quadrant, you know how we can make a 45 in each quadrant? It's going to go like this in each one. Okay, and same as here. It has a pattern. It has a pattern. So the domain says you cannot use 90 to 70. 90 is the same as pi over 2. 270 is the same as 3 pi over 2. But if you look at this, we could use 2 pi over 2. We did use it at pi. We could use 4 pi over 2. Up there was your 2 pi. So we could use the even ones. We couldn't use your odd ones. So to get the domain for a tangent, we say the domain is all real except for when x is n pi over 2, where n is an odd integer. This is really, really important. And let's see if this makes sense. If I put a 1 in here, I get pi over 2. If I put a 3 in here, I get 3 pi over 2. If I put a negative 1, I get negative 1 pi over 2. And a negative 3. negative 3 pi over 2. See the asymptotes here? If I put an even number in there, I'm ending up on the pi or the negative pi or the 2 pi. I can use those. So my domain for my tangent says, and you're going to have to get used to writing it like this, all real numbers except, that slanted line means except, where n is equal to, where x is equal to n pi over 2, and n is an odd integer. This is not a continuous curve because of your asymptotes. Okay? What's your range on this? All real numbers. Good. They keep on going and going and going. And your asymptotes fall at, are they y equals or x equal lines? X equals where n is an odd number. At my 1 pi over 2, at my 3 pi over 2. All the things that I cannot use in my domain will be where my asymptotes are. Does that make sense? Right? While you're digesting that, the reciprocal of sine. So this is how we start. I want you to sketch your sine curve in here. 0. Well, I don't have your sheet, but I'm just going to use, you're going to do it on here, and I'm going to do it up here. So your sine curve goes 0, 1, 0, negative 1, 0, 0, 1, 0, negative 1, 0. Put this in a dotted line. Okay, to get your reciprocals, it's easier if you draw the curve that you know first. Now, take a look at your zeros. This is key. Your 0 is, when we write this, if I look at my sine of 0, I'm 0 over 1, right? I'm just going to put these over 1. So what happens when I take the reciprocal of a 0 over 1? It's undefined, right? I can't divide by that. So when I go to find the reciprocal of sine, I'm not going to be able to use my zeros. So these guys become asymptotes. I can't flip those over because I can't divide by 0. That's the first part. Now, the second part is you just draw your curves off of these. This one is going to go like this and stay within the asymptote. This one stays within the asymptote. This one is going to stay within this asymptote. See it? There's your cosecant curve. It's not a continuous curve. It is a function, but it's not a continuous curve. It has asymptotes. Okay, all your reciprocals are going to end up with your asymptotes because you do cross the zeros, and you can't flip those over and divide by a 0. Now we got to get the domain down pat. The range, can anybody tell me what the range is for this? Not well, look at the blue. Your range for this guy, your range for your sine was this.
Negative.
Okay, so this one's going to be what? Negative infinity. Good. So right up to here, to negative 1. Or 1, you got it, to infinity. Very good. Very good. Do you see what Brianna did? She's the opposite. This is your sine from 1 to negative 1. Doesn't your cosecant use the opposites of these? They come from negative infinity, stops at negative 1. Starts at 1, goes to infinity. Now let's see if we can get the domain. The domain says all real except when x is, let's see, it's at 0 pi, it's at 1 pi, it's at 2 pi. So we're going to say n pi, where n is any integer. Any integer. Good, makes sense?
what you read for all domains.
No, each domain is a little different so far, because we have to go by this. We have to go by where our asymptote says we can't use. Our asymptote says you can't use it at the 0, you can't use it at the 1 pi, you can't use it at the 2 pi, therefore you can't use it at the 3 pi, any pi. So any pi. Hello, Mrs. Horn. Hey. Yes, I do. Okay, sure will. Okay, all right, thank you. Yeah. Get him to attendance at the end of the bell. So do we see how we're going with this? Yeah? Okay. Obviously you don't have a lot to do tonight, but tonight you're going to do your secant, and you're going to do your cotangent. And you're going to tell me the graph of its reciprocal, and